So we've got Josh Combs here, and I'll just let him get going. Thank you.
Yeah.
And how about we and is the sound working? Can you hear me?
Not yet.
Oh, it's probably this. Turn it up just a little in the audience.
Hello, hello. Hello. Hello.
Yeah.
Is that a bit better?
Yeah.
Okay, great. And
Can the online people hear it?
online?
Yep. We can hear you.
Excellent. Okay, yeah, so my name's Josh. I'm now at CU Boulder. I've been all over the shop. Here at CQuick as a postdoc. I did my PhD in Australia, in Canada, and I've been everywhere. So today I'm going to talk a little bit about quantum sensing and why the funny title. Well, this is actually the first time I've ever spoken about more than one topic in a single talk. I know that's pretty common for experimentalists. They talk about 100 things in one talk. So this could be a complete disaster, and so apologies. But that's the funny title. I didn't know of any way to unify these disparate things, so I'm just going to talk about two things. Why the spooky title? Well, nothing in particular, but I do like funny talk titles. So I once gave a talk on model reduction and adiabatic elimination, which was Hilbert, I Shrunk Your Space. March meeting talk, which was 2019, an odyssey into Hilbert space. And so I kind of like these talks, even though they're not so useful. So yeah, today I'm going to talk about sub-universal variational circuits. And I think this is a nice way to think about how can we compare circuits that we can't necessarily prove quantum advantage to some class of circuits that we can perform better, which might be better than classical circuits. And then the second part of the talk, I was actually going to spend most of my time talking about phase estimation for SUD. And this is like in the context where you're not allowed to do a controlled SUD unitary. You just have applications of SUD. Something like a generalization of robust phase estimation for the people who know about that. But I realized that I promised to speak about this. So I'm mostly going to talk about this, and then at the end I'll sort of mention this. And they're actually related things. They're not disparate things. They're intimately related. So that's what I'm hoping to cover today. Please interrupt, and we'll get started. So this work is with a undergraduate student, Gull Weitz. He's at CU in applied math, and he knew nothing about quantum mechanics before we started this. He'd taken linear algebra and said that should be enough. And from there, he sort of read 3 chapters of Mike and Ike and worked through the problems and started reading the QAW literature, and even worked his way, or partially worked his way through one of Matt Hastings' papers, which I think is pretty impressive for an undergrad. So I think we've heard a lot this week and you know, over many years about the promise of variational circuits, and many companies are hitching their cart to the NISQ and variational circuit horse, I guess, and maybe not Psi, and that's a great thing. But the question is, even if you look at that just from an economic perspective, is that the right thing to do? So, you know, can I build some other kind of computing device that would be, at least in terms of dollars spent, more efficient? And another question that at least I'm interested in from the perspective of quantum foundations and quantum computing, can we actually demonstrate that there's anything quantum happening or anything non-classical happening in these circuits? And if you look at the literature, essentially there's 2 approaches to this. One approach is to compare variational circuits to just guessing the problem. So, you know, maybe in the context of, I'll talk more about this shortly, but the context of constraint satisfaction problems like max cut, you know, can we just guess the answer and see how well quantum algorithm works for that. And then there's, other kinds of things where you do a relaxation of the problem and, using STPs and you can get quite good solutions to these problems. But neither of these are sort of in the same flavor as the current NISQ algorithms that we're looking at, like QAW. If you don't know what that is, don't worry, we'll talk about that shortly. So this is experimental data from Matt Harrigan's paper. So this is the Google team. So on the y-axis, we have the quality of the optimization solution. They're trying to solve some optimization problem. And then on the x-axis is the number of qubits. Up the top is data collected from a quantum virtual machine. So it's just a quantum simulation, no noise. And then the lines below are data collected from their hardware. And you can see in the way they've scaled this cost here that for sufficiently large number of qubits that the solution, well, maybe not this hardware grid, but the other solutions are approaching just what you would get from random guessing. So adding more qubits is not necessarily a good thing. We've heard that many times this week. You need to increase the quality as well. Perfect, if you could just get the answer to your problem, then perfect is one up here. And so it's hard to say whether actually anything, the quantum computer is actually doing anything quantum or if there's any interesting computation going on here because we're somewhere between perfect and random. And this is in the noisy case. Of course, if you had a noiseless quantum computer, then things are looking a lot better. It's a bit more promising. And of course, we know from the theoretical results that that's expected. Another way of looking at this problem, this is from Johannes Otterbach, his paper. This is now we fixed the problem size. So I think this is 19 qubits. So we're sort of cutting across this part of the x-axis here. And then they're examining the problem in terms of the number of goes they get at solving the problem. So, they've had literally no goes at solving the problem here and then one go, so on up to 50 chances of running their algorithm. And you can compare this to random guessing, and that's the red line down here. So what's the difference between the green and the red? So this is empirical. I'm guessing this is, I haven't actually got to the bottom of this, but I'm guessing this is a difference between sampling with and without replacement, perhaps. That's the only way I can make sense of that. But in any case, the more random guesses you get, the more likely you are to get the correct answer. So the bottom line here makes sense. If you run the simulation on the quantum virtual machine, then of course the more tries you get it, the better you get. And then when they run it on the hardware, things of course look better. But it's hard to say whether it's there's anything quantum about that. So here is what one of the good classical algorithms does. It gives you this sort of performance guarantee of this red line here. And on this thing, this is just an artist symbol. I'm not an artist, but this is my impression of what it would do here. So why are we bothering with all this? Well, as the problems get larger and larger, it's possible that these kinds of hardware solutions or the kinds of algorithms here could be useful on really large problem size, and even if the solution quality is not that great. But again, as someone who's interested in the quantum aspects, I want to know, is there anything quantum about this? Could I do the same with classical hardware? So I'd love to have a band of disallowed values, as in there's some classical protocols that are similar in spirit to these quantum variational things that I say, well, if I can get the cost or this approximation ratio in this band, then that's effectively classical, and we should just really not bother about it and build a classical variational machine. And so that's the spirit of this. So another way to say this is that the performance bar for random guessing is like asking me the answer to the solution. That's not a good thing. And then the GW, like the STP solution, is like asking to read higher enough. And so she's going to give you a much better answer than I am. And it would be nice to have something in between. So something that has the spirit of a variational algorithm, and it's a fair comparison. And it wouldn't prove that it's better, but it would give you evidence that there could be some quantum advantage, or at least set a higher bar than random guessing. The way forward, at least in my mind, is to take a page out of quantum computation or quantum foundations and think about the hardness of the things that we're doing. And so here, I think it's believed right now that contextuality is one of the key ingredients that makes quantum computation difficult. We know there's arguments against superposition. We know there's arguments against entanglement being the sort of absolutely most important thing. So, and this is related to things that people have thought about, like the negativity of the Wigner function. And so in the context of qubits, you can just define these discrete Wigner functions. So this is like the Wöhler's Wigner functions here, and they can be usually the Pauli eigenstates can be positively represented. The Y eigenstates have these sort of off-diagonal things. And then this is like an operator basis. You would then express all the transformations. So things like Clifford gates would be positively represented, and they would take positive states to positive states. And then the measurements, so that was the states, and the gates can be represented in these sort of quasi-probability distributions. And then the measurements can also have a positive quasi-probability distribution. And a really easy way to see why this is efficient to simulate is then if everything's positively represented, then you can just do Monte Carlo sampling. And so that's one way to think about it. Of course, if you have states that have negativity or gates that induce negativity, so something like a T gate, then you would not be able to do Monte Carlo sampling. And so one of the tricks that people use is they just sort of take the absolute value of the negative things and renormalize the probability distribution. And that gives you some way to do Monte Carlo of things that are sort of more quantum than the Cliffords. Any questions about it? So in the sort of the big picture, what we'd like to do is do variational circuits with things that are not universal. So things like Pauli preparation, Cliffords, and Pauli measurements, which we know are easy to simulate, or match gates, so the kinds of things that Akimas has thought a lot about. And so this is equivalent to like fermionic linear optics, and you can make that universal by adding like long-range swaps and things. Or if you're more of a optics person, you might think about Gaussian input states at most quadratic Hamiltonians, and then linear detectors, so things like homodyne, heterodyne, or IQ measurements. So that's the sort of where we're heading. So for these variational algorithms, they all look pretty similar. You have some quantum circuit at the bottom, and then some cost function. You get samples, you run your circuit, you get samples of that cost function. You set some threshold. If you haven't met the threshold, you use a classical optimizer to change the circuit parameters, and you rinse and repeat. And so this is the example of QAOA. And all I'm suggesting is we replace that quantum circuit with something that's effectively classical or efficient to simulate. And then make the comparison between these two. It doesn't have to be one thing. So in this talk, I'm going to focus on classical stochastic matrices, not doubly stochastic, which is what we often think about in quantum. But you could imagine, well, at least when we started, we were hoping to sort of work our way up and increasingly get more quantum and see what happened. But yeah, it's finite time, so we just stuck to this. Okay, so let's get to the problem. We'll start with max cut. Imagine, hands up, everyone's familiar with max cut or QAOA. Okay. All right, we'll just go through it quickly. So this is a cartoon picture. We sort of will solve the problem in the context of villages connected by roads, and the villages are going to be either wood cutting or mining. And then there's some important constraints that, so first of all, we want to maximize global trade. However, the woodcutting villages only like to trade with the mining. They don't like to trade with other woodcutting villages. And the villages can only trade if they're connected by a road. I'm feeling like I'm about to get a shock, Andrew.
No, I'm just very amused, and my mind is going to the latest Mad Max movie where there's like Bullet Town and there's. Anyway.
Okay. Next time it'll be a Mad Max analogy.
Very good.
Yeah, so we've got, these villages, they're connected by roads. So these two villages are not connected by roads, so they can't trade. Okay, and our job is we want to maximize, because we're capitalists, we want to maximize global trade. And so one way to do that is to try and assign, whether you're a wood cutting or a mining village. And so here's a pretty good, like a bad assignment would be wood cutting, mining. Okay, so because here we've got disagreement between these two. So this is a wood cutting and a mining, they can trade, wood cutting and mining, they can trade. However, if I had all wood cutting and all mining, then there's going to be no trade happening. And so of course, this is a problem on a graph, and that's we're looking at, maybe that's the next one. Oh yeah, so this is the kind of thing that QAW aims to solve. And it has these certain circuits where I'm sure some of you are familiar with these. There's like these cost operators and mixing things, and you do multiple layers of this, and it ends up solving one of these problems. We know that that's the case because Fahy and Al showed that limit that the number of applications of this sort of circuit primitive goes to infinity, then this is like the adiabatic algorithm. And for small p, I think p equals 1, it was they showed that the approximation ratio for a 3 regular graph was 0.6 something. So it does pretty well. So the trick with this is, how do you if you don't know the answer, how do you figure out when you've got a reasonable answer? And so that's really the whole deal with this. So in this setting, we'll take our quantum circuit, we'll run it with some sort of parameters, we'll collect a bunch of samples from that, and we'll be able to compute the effective cut on this graph. So this is like the disagreement between the, how many villages will, how many edges on the graph will we be able to get to disagree. And so this is like a sample from a distribution. So you can compute the distribution and then look at the minimum cost, or the maximum cut that we're able to get of this graph, the disagreements, and then perhaps optimize over this using the classical optimizer. Okay, so going back to the idea of how do we compare this with classical things, we know for classical reversible computing that gates are performed by permutation matrices, and over in quantum land, gates are done unitarily. And if you take the convex hull of the permutation matrices, you get like the doubly stochastic matrices. And they're like the sort of like the CPTP maps. So what's the difference between the doubly stochastic and the stochastic matrices? So if you have, if you have a, just let's consider a single bit. If I am in the state 0, for a doubly stochastic matrix, the probability to transition to the state 1 is the same as if I'm in the state 1, it's the probability to transition to the state 0. So there's this like symmetry between these things. So it'd be like the bit flip channel. That's an example where you have the symmetry between 0 and 1. The stochastic matrices are a little bit different. There's different transition probabilities. So the probability to go from 0 to 1 is not necessarily equal to 1 to 0. And in the context of quantum mechanics, we might see this in amplitude damping channels, for example. And if you're in contact with some thermal bath, there's different up and down transition rates. Okay, so for a single qubit, so I'm using Dirac notation here, but of course, when I'm writing a state, this is a mixture, not a superposition, really just mean a vector. A stochastic gate is something of this form. It's a valid gate if the columns sum to 1. And so this column sums to 1, this column sums to 1. There's 2 parameters here. And you can see that when I act on 0 and when I act on 1, the final states are different or could be different depending on P and Q. Oh yeah, you might think this is just a mathematical curiosity, but actually people build these things in the lab. So this is a PRX from, I don't know, 5 years ago now. And so this kind of hardware exists and people are building it. I think the motivation for it is building physical neural nets. They want to be able to have a bit that has some probability to flip, and then they make that into some sigmoidal function. But it's not. This is not fictitious. You could build this, and this is, in some part the motivation. Like, why are we building, NISQ quantum computers when you could probably pay a lot less money and get these guys to build something else if it works better. Okay, so let's look at max cut on this graph here. There's 2 edges. We want disagreement. Obviously, the solutions are going to be, the bit string has to be 0 and 1, or 0 and 1. So they're the 2 solutions. We'll start in the all 0 state. We'll apply our stochastic matrix, and then we go through our iteration, and we get. So this is the sort of ideal landscape. Sorry about the size of the fonts here. 1 probability here, another probability there. And the 2 extremes here, the probability is 1 in 1 bit and 0 in the other, are the optimal solutions. And so, of course, you can just use the same machinery you would use for learning in your, whatever you're doing in your current variational algorithms, and get some stochastic sampling and do whatever gradient descent or whatever optimizer you're using to find the optimal points, which are here and here. Okay, so that's not exactly what we're proposing to do. We want to do something slightly more sophisticated. And so we're actually going to take a 2p-bit probabilistic bit gate as our primitive. And it only has to be a stochastic matrix. So I don't, generally for reversible, you want a 1 in every row and column to be a permutation matrix, but here we just require the columns sum to 1. So we have 4 independent parameters here. And why choose a stochastic matrix of this form? Well, we know that generally for max cut, we want disagreement with the edges. So we don't want 0, 0 or 1, 1. So let's just from the outset make the ansatz that we want to penalize those. And we're going to I don't know what's the opposite of penalizing, reward, I guess, reward transitions to these states here. And so that's what's going on in this stochastic matrix. If you multiply the column vectors by that, you'll end up rewarding transitions to these 2 favorable states. So then what's our circuit ansatz? If you have a 1 regular, say something on a line, then you would just do 2-bit stochastic matrices between the things on the line. So if you had a 3 regular graph, then, well, if your bits are on the line, you would have to do these sort of non-local gates. But of course, we know classically doing things non-locally is not a big deal. It's a very low cost. So you can always just think about doing them on the hardware graph. Basically, I mean, here I'm not talking about C-naughts, I'm talking about these probabilistic, CZs. I'm talking about these probabilistic gates on the hardware graph. So we've given ourselves a bit of an advantage here. We're letting ourselves do things on a hardware graph. So that's actually easier than something like QAW would do. Moreover, we've chosen a clever ansatz. I think that's probably allowed. We also have more parameters, right? So I showed you 1 p-bit gate has 4 parameters, but that only scales with the number of edges in the graph. So it's a linear scaling with the number of edges. But we're restricting ourselves to depth 1. So we're going to have a depth 1 circuit. And if I show you the results here, so we considered complete graphs and 3 regular graphs. And this is just numerics. We're sort of in the process of looking at like first step Markov analysis to see if we can get some improvement away, like proven improvement away from random. But you can see at least numerically, if you compare, so Goal likes to call this PAOA, so probabilistic instead of quantum. And so the PAOA are the solid lines, and you can see it's for the complete graph is basically sitting on perfect. And for the three regular graph, it's, you know, fluctuating up and down. There are differences. Again, this is numerics. You shouldn't believe it too much, but basically what you're seeing here is that this really simple, completely classical variational ansatz is performing as well as QAOA. We didn't even have to go to things like Clifford's and match gates to sort of start to push up the bound from below. Yeah.
That's QAOA on a perfect.
This is perfect. Yeah, that's
So
right.
it would even work, I mean, even if you had, it's not even about NISQ, it's about the algorithm.
Yeah, that's right. So I think if I understand Ivan's point, he's saying, well, you go back to the earlier results from Google. Here, this is, I'm comparing everything to sort of the ideal case rather than running on hardware, which is significantly worse. Yeah. Okay, and if I remember, yeah, that's right. So that's basically the point I wanted to make here, and I'm sort of curious for this. You know, there's no proof here, so you should not trust anything that I say. But in the spirit of this section, it's evidence. So I'm curious about evidence with other variational algorithms. If we replace them with sub-universal things, how do we do? Do we do like? You know, I think there's a lot of mounting evidence against QAOA for many reasons, but what about other things? What happens if we do something similar in spirit? So I might pause here and see if there's any questions related to this before moving on to unrelated topics. Yeah.
So the results of Hastings, for example, and other classical algorithms like threshold edge, other curve and whatnot, do something like vertex.
Flip a coin, yeah.
Possibly some form of correlated with similar correlation. So up to the variational part, we're doing the angles. Any comments on the connection there? Or?
So I mentioned this to Alexandra Koller, and her first point was, I bet you could prove that you can embed this into Hastings. So like, you know, consider a larger instance of Hastings, you know, his formulation of his algorithm, then this would be could be embedded into that. I think that's a really cool idea, but yeah, I'm not sure I'm the right person to prove that.
Maybe more of the whole framework.
Yeah. Complaints, criticisms? I mean, give it to me. Yeah.
So I'm not familiar with QAW and how it's used, but essentially the final result here is going to be some bit string, which is supposed to solve.
Yeah, that's right. Some binary string, yeah.
What happens if your target is some kind of quantum data?
Yeah.
Or something like that. I mean,
yeah, I think that case is, you know, way more compelling. Like, I think that, you know, if the output's a quantum state, then, you know, presumably as you add more quantumness to the circuits, whether that's, you know, T gates, or if you're in match gates, whether it's, you know, other universal set, I think it's a good point. And again, I'm still curious to see, like, does that play out that way? I'm not sure. Yeah.
I mean, maybe you're going to say more about this, about the question of variation, but is this something particular to QAOA? I mean, is it always the case that if we were to do a variational algorithm that, you know, we could do a classical stochastic, you get pretty damn close, or is it the nature of the algorithm itself?
I would love to tell you, but I have no idea. I think there's a lot of optimizations that we did, like, you know, this, oh, sorry.
But that's fair. I mean, all
Like,
fair in love and war.
Yeah, that's true.
Why not?
You know, like picking this gate is really, this is a depth one circuit, right? There's only one layer in this thing, and that's quite surprising. And you know that there's going to be cases where getting disagreements actually not optimal. So you might add extra cell elements in, or but yeah, I don't. Yeah, I think it's an important question. I don't know how to answer it. If I did, I would probably have a really fancy paper. Okay. Well, I'm going to move on. So now for something completely different. So encoded phase estimation. So this is sort of the intersection, like phase estimation that people talk about in quantum sensing is really intimately related to cutoff or phase estimation. It's the same thing really, just you're not allowed to do controlled unitaries. One of the issues with quantum metrology, whether it's atomic or optical, is you have these noises that destroy any quantum enhanced scaling that you'd like to have. So you typically, if you're an optical interferometer, as you lose photons out of the waveguide or out of the beam, your quantum advantage goes away. And similarly with atomic interferometers, if you have like dephasing or loss of atoms, you start to lose your quantum advantage. And it's really interesting in the quantum metrology community, they don't really think about that. They just imagine that, well, it's a much easier goal than building a fault-tolerant quantum computer, so it should be okay. But I think it's true in some sense. I think you can build, we're all going to go, well, many of us are going to go through the airport and you're going to get the person who scratches you and puts the little thing into the spectroscopic machine. And I could imagine that there's going to be a quantum lab in a box, and that could have, quantum enhanced scaling. But many of the real world applications are not going to be neat like that. And you're going to need to do error correction, even in sensing. And so I think some people like Andrew and others who are expert in error correction could probably make a huge impact in thinking about some of these metrology problems in the context of optical and atomic interferometers. So there's two problems in quantum parameter estimation. And usually we hear about one of them, and that's called local metrology. In local metrology, you have, say, a phase or any parameter that you care about, and you know roughly where it is. So let's say it's here, and you're looking for tiny deviations around that point. And so this is usually the case in optical interferometers, things like LIGO. And you may remember back to your undergraduate labs where you locked an interferometer. So you had to like count fringes. And then basically all of these sensing experiments, you're looking for tiny deviations around this locked interferometer. So in the context of here, we can just call, a phase is, an angle, a phase is a parameter that's confined to this interval minus pi to pi, and it's periodic. So wherever you're pointing, you can always just call that zero phase. And so then you're just looking for small deviations around that. And because we're just looking about small deviations around that, we can just sort of blow up that interval and say that that's the whole interval, whatever the small deviations are. So we're trying to estimate the parameter on this interval. And this is really well described by the aerometric mean squared error, and that's bounded by the Kramer-Rao bound, which says that you have one on the classical or quantum Fisher information. And I think this is something that probably most people have run across. Something that may be less familiar is what's called global metrology. So now you have a parameter. It may also have an initial state. You might pass your probe through an interferometer and it may initially have zero phase, whatever. But the interferometer can impart any phase shift. So it could be minus pi, it could be plus pi on 4. It doesn't have to be small. And so the parameter now you want to estimate is on the entire interval, pi to minus pi. And it's no longer a good idea to use variance or mean squared error in that case, because the boundary wraps around, and we'll see why that's bad shortly. But let's go to a digression in phase, which is not something that we talk about a lot in quantum, not even in quantum optics. And it's pretty contentious. I know some of the people in the room know the long history of this. But let's just start with the sort of let's even go with the classical harmonic oscillator or quantum harmonic oscillator, but just think about coherent states to start. So we take so this is like the position and this is like the momentum of the harmonic oscillator, or if you're thinking about light, it's the two quadratures. And we're going to extend our harmonic oscillator out to some position and then let it ring around in phase space. So it's on this ring of constant energy. You can take the mean field, that's the classical solution. It's identical to what you would get for the classical harmonic oscillator. Cosine of x, sine of momentum, and do a polar decomposition on that complex number. And so you have a magnitude and a phase. And that phase is on the interval we want. And so that's what we're going to call phase. Any questions about that? This is just classical so far. Now in quantum, everyone's seen these Wigner functions or Q functions or whatever quasi-probability distribution you like. And that's really the sort of way of visualizing this harmonic oscillator in the phase space. And for a long time, people thought about phase in quantum optics is you would take your favorite quasi-probability distribution, change variables in this way, and then integrate over the radial direction. And what's left is the marginal distribution of phase. And this is, a bit quirky, but it's a reasonable way to think about things. And so here you can see that this is my coherent state. That's a two-dimensional Gaussian in the Wigner function. And if I sort of look at the sort of angular coordinate here, maybe I get a Gaussian, and that's what's sort of plotted over here. I don't know if that's in the right part of it. Should be pi on 4. Okay. Please interrupt if I'm being confusing or you're not understanding. So how does this relate to any of the sensing and interferometry? So for optical interferometers, you usually have like a simple one is this Mach sender, and you have 2 input ports. And the thing that you're sensitive to is differential phase shifts. So there's a phase difference between the 2 paths, and you recombine the signals and measure some operator, and that lets you sense theta, which is actually the difference in the path lengths between these 2 things. So you could imagine it's like θ1 and θ2, and you're actually measuring the difference of those, that you're not sensitive to the common mode. In atomic interferometry, you'll prepare a bunch of atoms in a ground state, you'll rotate them up, and then there'll be a magnetic field, and they'll precess, and you're trying to measure the precession. And that's also a phase, right? Because it can wrap around. In both of these cases, if that phase is small, then you're back in the local metrology case, not in the global metrology. And actually, these 2 things are identical. So maybe you know about the Schwinger representation. So this is where you have 2 bosons, or 2 harmonic oscillators, A and B, and you can write linear combinations of the annihilation and creation operators as a spin operator. And so that shows you that actually these 2 things are identical. So if you understand one, okay, there's differences in practice and there's very important things that you should do and understand about each. But if you happen to be good at one, then you can learn the other one more easily. So it's just a little hack if you haven't thought about that before. So if you solve something in one, you can usually find a very easy mapping to the other one. So we're caring about both of those kinds of interferometers. And now let's get to the quantum description of phase. And this has a long history. Dirac started thinking about this in 1927. And his approach was to take position and momentum. So just as we did the polar decomposition classically here, Dirac's like, well, why don't I do an operator polar decomposition? So we know that if you have position and momentum, you do linear combinations of them, you get the annihilation and creation operators. They diagonalize the harmonic oscillator Hamiltonian. So let's take them, do a polar decomposition of them. So this is Dirac's idea. And you get something like the square root of number, and then something that he hoped was the exponential of a Hermitian phase operator. That doesn't turn out to be correct. But let's just run with it for a second. And he was sort of hoping that you would then get a commutator between number and phase. So these would be conjugate variables in the same way that position and momentum are conjugate. That was like this. This has a really long history, probably the most related stuff to what I'm going to talk about, but I'm not going to dive into this, is like Susskind's approach to the phase operator. Susskind basically figured out how to do this correctly. It's not the only way, there's a ton of different ways. I'm not promoting one over the others, but it sort of matches with what I'm going to tell you. Simultaneously, I think it's maybe Fritz London, does anyone know? It is Fritz. Had this idea of coming up with phase eigenstates. We know that position eigenstates are delta functions in position, momentum eigenstates are delta functions in momentum, and the fact that whenever you draw two position eigenfunction and momentum eigenfunction, they intersect at one point, is sort of a graphical way of thinking about these two things don't commute. So London realized that if you took this equal superposition of the Fock states to infinity and put this phase in front of them, then this is kind of a phase eigenstate. And it's non-physical. You can see that it's got Fock states out to infinity. And we know that the wave function has to decay. This is not L2 of R, so you need the wave function to decay rapidly at plus or minus infinity. But then again, neither are position or momentum eigenstates. So this is no worse than position or momentum as far as a non-physical state. So how can we think about this? Well, roughly speaking, you can develop quasi-probabilities based on number and phase. And then in that quasi-probability, number states are positively represented, phase states are positively represented. And then things like coherent states actually have negative Wigner functions, which is kind of wild. But even if you just go to a cartoon picture, Fock states are rings in phase space of increasing radius. And phase states are just rays or lines in phase space. And they cross at some point, which tells you, graphically, they don't commute. Okay. That's all well and good, but without a way to measure phase, then it's kind of pointless. So there is this phase measurement. It's a generalized measurement or a positive operator value measure. It's the outer product of these things. And in 1995, Weismann figured out a way to do this in practice. And this has been demonstrated at optical and microwave frequencies. And so this gives you a way to actually forget about all the, if you want to, forget about all the arguments about phase operators and just think about what is a phase measurement. So you don't need to rely on the existence or non-existence of Hermitian phase operators. And so then you can get a phase distribution. So you take the trace of your state with this phase measurement, and that's your phase distribution now. Oh, wow, okay. Oh, uh-oh. You still got us on land? That's where we all want to be. Okay. Okay, so yeah, just reiterating, there's a phase measurement. You can do it in the lab. It's being done in the lab. And that gives you a phase distribution. So now we know what these are. We take the trace of our phase measurement, and that's the marginal phase distribution. So it would be like the position distribution. If you integrate out the momentum coordinate in the Wigner function, then you get the marginal position distribution. So what's the problem with the regular variance in phase estimation? If you just reiterating, if you have small shifts, there's no problems, you're okay. Big shifts, like you might experience in a quantum circuit, you have the following problem. As soon as I get to the boundary, then it wraps around. So when I compute the variance here, I'm going to get the variance is actually going to change. If I take my Gaussian state and just slowly displace it this way or translate it this way in phase, the variance will change. So you don't want the variance to change, right? It should be just a fixed property. So you have to go to the field of circular statistics and consider other random variables. So this is the sort of standard random variable that you would consider in circular statistics. When you do this, this is called the circular variance, then no matter how you translate this distribution, it will have the same variance at all points. And in our field in quantum information, Halevo really rediscovered this. And so in our field, we call some normalized version of this the Halevo variance. So that's the thing we're going to look at, and just to say, sort of make it a bit stronger, what I was saying at the start of this section, as you add losses or phase diffusion, then basically any quantum advantage you'd like goes away. And so this is a big problem for quantum metrology. And this is true for, I mean, there's nonlinear versions of interferometers too, so it also holds in those cases. And so I think we really need to think about encoding metrology in the same way that many people would be, oh, that's not quite right, in the same way that we're really interested in doing error correction on a quantum computer, because we think that ultimately that's the thing that's going to lead us to quantum computing. So here is the start of new research. This is work that I've been doing with a bunch of people, and to get to that point, we need to learn about modular phase. So already phase is modular on the interval pi to minus pi, it wraps around. So what do I mean by modular phase? I mean subintervals. So a phase, so here I would say that something is modular on this subinterval. If I had a parameter that was had a symmetry on these two wedges, then that would be a modular phase. It might be a bit weird to think about that, but if we go back to this picture of, actually maybe we'll go forward, and so on. So now I would divide the phase into 3 intervals. So here's an example of that. This is a Wigner function for squeezed vacuum. It's got, I think, 12 dB of squeezing. And you can see that it has a rotation symmetry. If I rotate it by pi, I get the same state. So if I go and compute the phase distribution, you can see that if I translate it by pi, I'll just get back to the same distribution. So the unique part of the distribution is this thing here. And so if I just focus in on that, I can sort of neglect everything else, then this is my modular phase distribution. That's okay? All right. So, what do you think the phase distribution of that's going to look like? Just to see if your intuition's working. Just see if you can unwrap the angular coordinates. So 0 is, the x-axis. So what is that going to look like? Maybe you've done that. And so you've got this as the modular phase distribution for that state. So we're just taking squeezed vacuum and you can rotate it continuously, and you'll see that these peaks kind of shift continuously and wrap around. So that's what I mean by modular phase. Oh yeah. So there has to be a rotation symmetry in this state, in phase space, and then that means that I can just consider sub wedges of phase. So this is what this would look like. Okay, so trust me, it's going somewhere. We had the phase eigenstates of London. The modular phase eigenstates are rotated versions of London's phase states, just on some on some grid. So here is the example of the squeezed state. And so it would have some modular distribution. You could work out what that would be in your mind. So this has an n equals 2 rotation symmetry. Here's an example where I have a 3-fold rotation symmetry. And so now what would the modular wedge be? It would be these kinds of, the states unique on this wedge of phase space. Okay. So we also need a way to measure modular phase. And so the way you do that is take the outer products of these modular phase states.
You're a case of use epsilon.
Yeah. Carl, oh God, it's the greatest Greek letter. It's very proud. Yeah. Actually, that's my go-to whenever I think of like what symbol should I use here. If I haven't used epsilon, I always remember Carl and use epsilon.
I'm sorry.
Yeah.
Are they worried about normalization or something weird?
They could be.
None of us feel good about the arguments themselves.
Oh yeah, they're not normalized.
Yes, then how the heck are we going to build a POV?
So the POVM is positive. So you could say the same thing about position. So why am I allowed to do position measurements?
Yeah, right.
Because they're not normalized eigenstates either. So what you can do is construct a Gaussian distribution over position eigenstates, and then take the limit where that Gaussian goes, and that's basically measuring the squeeze rate of that. Yeah, exactly. Yeah. Okay. Yeah, and so then the distribution is just, take the trace of these things, and you get your modular phase distribution. Okay, so all of this is, I'm heading towards error correcting codes. The rotation symmetry is going to introduce a degeneracy, and this degeneracy is what we're going to encode quantum information in. And so if you have a twofold degeneracy, you have a qubit. If you have a d-fold degeneracy, you have a qubit. So here we're just interested in the case of a qubit, we're just going to encode a single qubit. And we want to minimize the phase variance because we're going to do phase measurements. So we're going to take this Halevo phase variance, translate it into an operator. That's this approximately this cosine operator here, cosine of the phase. And then we're going to construct a Hamiltonian. So we want to find the ground states of this Hamiltonian subject to constraints. And I'm trying to remember who was talking about that. Was it Hank yesterday? Were you talking about like adding, I can't remember, someone was talking about adding constraints, like symmetry constraints to the whatever HEP problem they were interested in. And this is exactly the same thing. We're going to find the ground states of this. When you do that, there's many ways to do that. You can do that with Lagrange multipliers, or you can explicitly solve the recurrence relations. You get two solutions. So these solutions are the photon number distribution. Sorry, it's the amplitudes in the photon number basis. And so they go. So we did the case for n greater than 1. So n is the sort of modularity of the interval. So the minus pi to pi is n equals 1. Every n bigger than that is what we did. And if you put a cutoff in Fock space, then the amplitudes are distributed as the first part of the sine. If you put a constraint of mean photon number or phonon or whatever you're using, you get basically an Airy function as the envelope of the amplitudes. And down here, you can see that the Halevo variance is scaling as f squared. So this is variance, not standard deviation. So if you want to think about Heisenberg limits, the variance should go as, like if you think of Noon states, then it should go as like f squared. So you see that we're getting a Halevo variance that's scaling as f squared. That means we can estimate on any interval with Heisenberg limited position. And similarly, for the state where you've got a mean photon number, it's scaling is like the expected value of the number operator squared. So what do these things look like? Here's the sine. So this is the n equals 1. This column was known before our work. And then we've basically shown how to find the optimal states for other things for higher n. For n equals 1, you see the sine quite easily. For n equals 2, you can see every second Fock number is cut out. And so this is to do with this is a direct consequence of the phase space rotation symmetry. Whenever you have that phase space rotation symmetry, then you'll lose every second one. If you have a threefold one, then you lose every third one. There's two solutions shown there, ignore the orange. And if you take the extreme limit, where you have a 13-fold, so we've truncated the Fock space from vacuum to 13. And now it looks like a Noon state, except it's the single mode version that's called an ON state. And it has this, n-fold ripples in the phase distribution. So this is like exactly what you expect for Noon states. So in some sense, you see that we actually get back the kind of Noon story, if you're familiar with that. The point here is that these states in all of the Hilbert space are the ones with the minimum phase variance. And so that's going to be good for sensing, because if we have a large phase variance, we're going to be insensitive to variations of the phase. So how does this relate to codes? Oh, yeah, I think I said that. How does this relate to codes? So the fact that we have this rotation symmetry lets us construct a code. So here is a case. So these blobs here are examples with four-fold rotation symmetry. In our code, it's easiest to think in the plus minus basis. That's what's easy to visualize in phase space. The plus state is the red. So these would be like, if there were circular blobs, this would be a Schrodinger cat code. I've squeezed them, so maybe this is a squeezed cat code, but it could be anything. Then to the blue is the plus state. And if I do a rotation by pi on n, so in this case pi on 4, then I've done a logical gate. Okay, so that's how you do, that's the Z gate. And for X, I have to translate photon number in a certain limit. This is like one of the Susskind phase operators. So there's a trade-off in these rotation codes where your resilience to shift errors, so this is like photon loss, and your resilience to phase errors sort of trade off with each other. So here I have an n equals 4 code, and you can see that if I were to draw lines out here, that I can't tolerate a whole lot of phase errors. Fortunately, in many bosonic systems, phase errors are not a big deal. And it's actually photon loss, which is the dominant source of error. That's also true for mechanical oscillators and so forth. So basically, you find that the shift errors, you can correct up to n shift errors or photon loss or gain events. And you can correct at most a rotation of pi on n. And so a lot of this is work with Arne Grimsmo and Van Barajola, and also Victor Albert, Misha Woods, and Kyungju. So how does this work in a sensing protocol? The idea is you encode your bosonic system in one of these states with rotation symmetry. If we want to do phase estimation, they'd better be states that have very narrow phase variance. And that's why we went through all the song and dance about minimizing phase variance. Then they're going to experience noise. And if that, as long as that, say, let's just work in an idealistic limit, let's just say the noise is only photon loss or heating events, so for gaining photons, then we're not worried about phase errors. That's okay, because we saw that the logical operator was exactly these like phase space rotations. We can measure, and we don't even have to correct. We can just, this is the sort of, I'm not sure what to call it. It's not a, maybe it is a detection rather than correction, but it's not necessary to correct, and you can still get the Heisenberg limited phase estimates. So here's a little example of this, just to give you an idea of why I think it's interesting to think about these bosonic codes in the context of sensing right now. The two dominant codes at the moment are the cat and binomial codes. These are really nice codes for lots of reasons. They have a rotation symmetry, so they fit into this class of things that we're talking about. The codes that we were talking about before, these things with the sinusoidal envelopes, are brand new, not even published yet. You can see here, this is the logical channel fidelity. Sorry, this is the fidelity after recovery of the qubit. And then this is some error rate down the bottom here. And you can see, so, error rate lower is better. Okay, or, 1 minus fidelity. And you can see, compared to these standard codes, in some cases, we've got like 6 orders of, or more of magnitude improvement. So, just because people haven't explored this area very much, it's really easy to make big gains in improvement. But in the context of sensing, one of the, how do I interpret these results? These cat and binomial codes actually have very broad phase variance. And this explains why they're performing so badly here. This is the context of that. And I think I'm out of time, is that correct now?
I mean,
Yeah. So maybe I'll just say quickly, I'll just mention this thing because I did put in the abstract. So many of you will know about all sorts of things about QCVV. And a really important protocol that links to what we were just talking about is this idea of phase estimation. and in particular, this robust version of phase estimation. The idea is that you have a gate on a qubit and you want to tune it up. I'll do the context of a Y gate, but it can be any gate. So, Y gate's a rotation about this axis out of the board. And let's suppose there was an error, like I wanted to do a pi rotation, but I've got an epsilon error. The rough idea is I apply the gate m times, and I can amplify that error coherently. And so, Y commutes with itself, so it's pretty easy to decompose things in this way, where I've got the ideal rotation applied n times, and then I've got the error that's being magnified by n times. And so this is really the trick to phase estimation. So I won't talk so much about the robustness, but maybe I'll just sort of say what we've done. This protocol was basically for a single qubit. When I was at Rigetti, we figured out how to do this for 2 qubits, and you can look at the code online. Since then, we've basically figured out how to estimate all the parameters in SUD with Heisenberg limited precision. And it looks very similar to the same kind of things that you've probably seen when people talk about gate set tomography. Oops. You have a preparation circuit, you apply your gate some number of times, and then you have a measurement circuit. So this is really exciting. Why on earth would you care about this? Well, imagine you have spent your whole time trying to build a encoder for some code, maybe the 5-qubit code, maybe short code, whatever. Now you can, we have this story in QCVV where we would like to do characterization of our 1 and 2 qubit gates. And then we imagine that reflects the accuracy of, reflects what we do when we compile larger circuits. And in this situation, you don't have to worry about that. You just take your subroutine, which might be an encoding circuit, and you do phase estimation on it, and you can see how well you've done in building that encoding circuit. So it's like a nice way to think about QCVV for larger circuits. This is joint work with a grad student at Caltech, Kyle Golshin, and one of my graduate students, Benjamin Marinov. Okay, I think I'll leave it there. Questions?
I have a question.
Yeah.
Hi, this is Andrew Forbes from UNM. So it's obviously very natural in these rotationally symmetric codes to think about one of our errors being a rotation. But could you maybe say a few words about the choice of trying to detect or correct against rotation errors versus just like number operator errors? Because I know that in the first paper on the binomial code, they designed the code around being able to correct number operator errors. Is that the same thing? Can I work between these two pictures and just go from one to the other and they correct the same type of physical event? Or yeah. Yeah,
no, good question. So let's just go back to qubit codes and think about that. So the way we think about errors in qubit codes is you construct an operator basis, so like the Pauli basis or tensor products of Paulis on many qubits, and then your code can handle some number of errors. And you could take a general channel, amplitude damping, or crazy correlated noise, and you decompose it into that Pauli basis, and then sort of figure out your decoding based on that. For all of these bosonic codes, it's the same. So for GKP codes, the natural basis is, so the displacement operators form an operator basis for the harmonic oscillator Hilbert space. And so in that case, it's natural to decompose something like a loss channel into displacement operators and sort of think about decoding the errors that way. In these rotation codes, it's very natural to decompose the errors into shifts in photon number and rotations in phase space. So the shifts in photon numbers are generated by, you can see on this slide here, by this, this xn operator is a logical operator, but n could be any integer 0, 1, 2, 3, 4, whatever. So I can take a loss channel or any channel for a harmonic oscillator and decompose it into shifts and into rotations. And so that's the way to think about that. And indeed, you know, as you said, binomial codes were designed specifically to correct certain loss events and certain powers of photon number. But I could also decompose them into this basis equally well to show that they correct the that they still correct things.
Got it. Thank you so much. Yeah, that makes sense.
Questions?
Hi, Josh. This is Sohaib from Zoom. Sorry, I couldn't be there in person, but I posted something in the chat while you were talking about the classical analog of QAW, the PAOA, I think you were calling it. So my question was, it sounded like the PAOA always has a fixed depth, depending on the edge set of the graph. A, is that right? And B, you made a comparison between that algorithm and QAW, and my question was, you know, how many layers of QAW were you considering in that comparison? And Eleanor posted a related question, which I'm wondering about as well, which is that if it is true that the PAOA always has kind of a fixed depth, is there reason, or you know, how straightforward is it to extend it to larger depths? And yeah, those are the questions
Okay.
floating in my head.
So let's see. Firstly, I didn't know you moved to Zoom. Is that the NASA office? Okay. So yeah, we just considered depth 1 because it started working at depth 1. So we initially had planned to do higher depth, and we thought that we might need to sprinkle in single bit probabilistic gates to, you know, for the cases where the optimal solution actually requires agreement between particular edges. But just because it works so good with depth 1, we just stuck with depth 1. I believe the comparison is with, I think, depth 6 QAOA. Does that sound, at least, does that sound plausible? I should have checked that before I presented these results.
Probably.
Yeah, so yes, I think you could consider higher depth in PAOA, and I think layer 6. So Eleanor is saying, how do we extend your approach to depth 1? Yeah, so I mean, maybe for the overview for how to extend the approach to beyond depth 1, then I just give this cartoon picture down here. So actually, maybe it's obvious to some of you that, you know, reversible, like our circuits are not even universal, universal for classical computation, because for classical computation, you need the 3-bit gate to be universal reversibly. Okay, so we're using, I mean, in this case, we're not even using this first layer, we're just doing the second layer, and that's not even universal classically. So we know it's not that great, but, you know, in principle, you could do multiple layers here, as shown on this slide. But maybe related to Eleanor's point, I mean, I think an open question for this, so we have the number of parameters scaling as the number of edges. And so it'd be really interesting, like that's, again, a huge advantage over QAOA, where you have, you know, 1 or 2 real parameters every round. What happens if you could, what would happen if you could just get with log of the number of edges? I think that would be pretty impressive. It's a smaller optimization space, and you'd have less likely to be overfitting. And yeah.
It's not a really formulated question, but, you know, there's this argument for the optimality of cat states for sensing rotations for Fisher information. And I'm wondering, you know, once you've restricted a certain, you know, subsets of things, right?
Yeah.
How do you then connect it back to the Fisher information? Or can you? I mean, I'm sure you can, but how do you do that?
Yeah, so these states have scaling, like the variance scales the same way that the optimal states with Fisher information scales, but they're just sort of incomparable problems, except for that one example that I showed you, where sorry for the last. Here, where we're sort of increasing the module, or decreasing the size of the modular wedge. And when it hit the photon number cutoff for these Sine states, then it became this 0 plus n, which is the sort of the single mode version of the noon state. And then that would be the thing that if you did a Fisher information, this would be the optimal state.
I see.
So there's kind of like a sequence. So at no point, if someone held a gun to your head and said sense modular, if you have a cutoff of 60 or 13 or whatever, and sense an n equals 3 modular phase, would you ever use the noon state? Because that will perform worse than this one. But in that limit, it would agree.
Okay, thank you.
My question is also on this penultimate tale from the crypt here, quantum error correction. First of all, a comment. I agree. I think quantum error correction and quantum sensing, bringing those together has the potential to really become a golden age in the near term. And I would encourage young researchers in the audience here to think about this as an area where you can make contributions when there's a lot of low hanging fruit.
Yeah.
My question is, in ordinary banal qubit based, quantum error correction, and citing a series of developments that happened over the past year in terms of what are called good quantum codes, which are codes where the ratio of the number of encoded qubits to physical qubits goes to some constant as this infinite code family grows. So for example, the surface codes do not have this feature. If you have a surface code patch, you make it bigger, you have a better protected qubit, but it's just one qubit. But there are codes where as you make it bigger, you also get more encoded qubits as well. So I was wondering if there, the example you showed with these modular phase states, as you increase your capital N, you're still just encoding one, degree of freedom, if you will. Here, is there a notion or being able to generalize this to like multi-mode squeeze states or something like that, where you can encode more of them? And if so, do you see any kind of metrological use for such things?
Yeah, maybe. So I can answer. I feel like there's two parts. So first of all, you can encode a QDIT into a harmonic oscillator. So even in the GKP case where they had a translation symmetry rather than a rotation symmetry, they showed how you could do encode a QDIT. Similarly, in these rotation codes, you can find, instead of a two-fold degenerate ground space, you can find a default degenerate ground space. So but I think that's like part of the question. But then your point about multi-mode codes, for sure, I think that there's a lot of evidence already. I mean, even in linear optics, if you just think of like the sort of naive KLM type encodings, then the dual rail encodings have huge advantages with respect to how easy it is to do gates. And then there's other reasons to do them for sort of like post-selection reasons. And so I think, similarly for these bosonic codes, generally the multi-rail versions, or they call them, what do they call them? Anyway, the multi-rail versions perform better than the single rail versions. And the gates are easier and all that.
Yeah, I brought up multi-mode because I was imagining sort of tensor product structure, which you don't necessarily get with qubits, from qubits to qubits. I was wondering, you might want to have this sort of tensor product structure of your logical encoded information or something like that.
Yeah, and I think this is interesting in the context of the sort of multi-mode cavities that the people from SQMS are sort of interested in as well.
One more question, if anyone has. Sure. Yeah.
So I'm just thinking, why do you also have the mirror reflection symmetry? So since two mirror reflection is a rotation, so it's more basic than rotation symmetry.
Oh, like in this case here, there's a mirror.
Yeah.
Yeah, but when you go to the n equals 3, you don't have that anymore. This would be the plus state for the code, and the minus state. So there's no reflection symmetry in this case. So for all the
when
even,
you do the combination of those two general form.
that's a really that's a
I sort of figured, I wonder if the mirror symmetry state is easier to produce than, like you said in your paper, the breeding and the rotational symmetry.
right.
Then you can do the mirror symmetry and then you encode more symmetry.
Yeah.
And include the rotation.
Yeah, these are what you're pointing at, people are starting to think about. So this is another reason to jump in. So you know, in the plane, there's only so many symmetries you can have. And so people have even sort of thought about like what happens if you had a quasi-crystal code and where you have like approximate symmetries and things like that. So yeah, I think it's a great, but to answer the thing about the mirror symmetry, in this case here, just with these two things, there's like, in some sense, there's a kind of a translation symmetry too. If you like, I could imagine adding another lobe on, then you would have both the rotation symmetry. Like imagine there's another coherent state here, then you could have both like some sort of pseudo translation symmetry as well as a rotation symmetry. I think that's, yeah, and a mirror symmetry.
All right, so let's thank Joshi. Let's break until 3:30, and then we'll come back for some discussion.
Mac can still move, but we'll just say it. So Mac, you need the 3 qubit in like a top of your left right qubit. And so yeah, it's kind of weird.
Yeah, absolutely. Maybe it was already in the, I'll just, I will read it. After the end of each day, so it's fine.
I didn't get much of the details of the PIOA. I was curious. So it's classical circuits. What does that mean? Say, like, is it classically